There, Mr. Sutton here, bringing you the Algebra 2 6-1 Part 1 homework solutions on exponential growth and decay. In this one, we're focusing on graphing exponential functions and also figuring out growth and decay rates. For the first few problems on this homework, they want us to determine whether the function is exponential growth or decay, and then graph it out. So for this one, we have a b value of 6. Since that's bigger than 1, that means this function is growing with every increase in the x, so we have exponential growth. Let's make a table now. We're going to use -2 through +2 for all of these tables. So we've got 6 to the -2, which is 1 over 6 to the +2, or 1 over 36. Next up, we've got 6 to the -1, which is 1 over 6. 6 to the 0 is 1. 6 to the 1 is 6. And 6 squared is 36. Graphing all of that out, we've got -2 comma 1 over 36, which is very close to the x-axis. And then we've got -1, 1 over 6, which is also very close to the x-axis, but a little further away than 1 over 36. Kind of impossible to tell at this scale. Then we've got 0 comma 1, which is a little bit higher up. And then 1 comma 6, we can actually fit there. I had to make my y grid lines go by 6s because we have such a fluctuation in our range here. And finally, we have 2 comma 36. This is the one that really forced my hand. This is a big value up here. So now graphing that with our horizontal asymptote on the x-axis, here's what our exponential function looks like. For this problem, determining if it's growth or decay, we have a b value of 1 over 6. Since that is between 0 and 1, that means this is exponential decay. Plugging that in with some x values now from -2 to 2, 1 over 6 to a negative exponent is going to make it 6 over 1 to the positive version of that exponent. So 1 over 6 to the -2 is really just 6 squared, which is 36. And then -6 to the -1 is 6. Anything to the 0 is 1. Anything to 1 is itself, so 1 over 6. And then dividing by another 6, we end up with 1 over 36. So graphing all that out, I'm going to be going from down here up to something that's going to accommodate this 36. So we got -2, 36 up here, and then -1 comma 6 right there. So my grid lines are working out well so far. 0, 1 is kind of close to the x-axis. 1, 1, 6 is closer. And 2 comma 1 over 36 is so close that it's kind of hard to draw at this scale. So we have our decaying exponential function going through those, and that's it for this one. For this problem, I have a b value of 4/3. That is actually bigger than 1, so that means this is actually exponential growth. So if you see a fraction, you can't assume it's decay. You always have to check to see how it compares to 1. So graphing all this out with a table from -2 to 2, I'm actually going to do this on the calculator. I mean, this to the -2nd power is just 9 over 16, but I mean, what does that actually mean as a decimal? I'm going to get decimal versions just to make this a little bit easier to approximate on my graph. So let me call up Desmos here. Desmos, here we go. Let me just plug all of these in now. And I'll just make a little function so I can do this easily. So I'll call this f of x equals parentheses fraction 4 divided by 3, close that and raise that to the x power. And now let me just plug in a few things. So -2 comes out to about 0.56 and some change. If we plug in -1, well, that one I can do in my head. That's just 3 over 4, which is going to be 0.75 on the dot. Anything to the 0 is 1, so that's pretty easy. This is 4/3 to the 1, so that's just basically like 1.33. And then if I raise this to the 2nd power, I can do that on the Desmos here. That comes out to about 1.78. So I've got some pretty fine decimals here. I'm going to make my y values go by, well, something that'll get me from 0 to 2. So if I go by maybe 0.25s on the y-axis, I can get a little bit of accuracy with these. So we've got -2 comma 0.56, which is somewhere around here. -1, 0.75 is right there. 0, 1 is up here. And then we've got 1 comma, and then 1.33 is somewhere in here. And finally, we have 2.178, a little bit above, or 2 comma 1.78. That's a little bit above 1.75 right here. And then let's draw that. And this doesn't go back far enough to see it really approaching the x-axis. It's because we're so zoomed in, but it is. There's still an asymptote there. For this problem, we're told that the number of salmonella cells on an egg after t minutes is given by y equals a times 4.7 to the t over 45. That's a comforting thought. Yay, salmonella! And a is the initial number of those cells. We want to know by what percent does the number of those things increase each minute. We don't actually want to know, but we're going to find out anyway. So let's begin. If we're trying to find the growth rate, and this is going to be a growth rate, these things are growing, we're going to have to convert this into a times b to the t form, and I'll use my exponent rules. So I'll pull this exponent in to be 4.7 to the 1 over 45, all of that raised to the t. And now let me figure out what 4.7 to the 1 over 45 actually is, and that'll tell me my b value. That's my next step. So 4.7 exponent 1 divided by 45 is about 1.0350 if I round it to 4 decimal places. And now I can split this up into 1 plus 0.0350. This is basically 1 plus r, this format here. This is growth form. And then I just move my decimal over 2 on that decimal to get me a 3.50% growth rate of salmonella cells. For the next few problems, they want us to rewrite the function given in either growth form or decay form, state the rate, and then describe the end behavior. So to get this one, looks like it's going to be growth form, but let me just double check. I'm not actually sure on this one. You never really know until you find the b value. So let me pull the 1 over 6 power in to be with the 4, and then we have just a t out there. So whatever 4 to the 1/6 is, that's going to be my b value. Let me go to Desmos for that, clear out what I had before. So we have 4 exponent 1 over 6, and that's bigger than 1. It's 1.2599, which I can split up into 1 plus 0.2599. And this might look familiar to you if you remember the lesson. There was a problem where we had 2 to the 1/3, and it came out to this. This is actually 2 squared to the 1 over 6, but if you multiply the 2 and the 1 over 6 together, you do actually get 1/3. So it is the same number. We have a growth rate then, since this is bigger than 1, a growth rate of 25.99%. And for the end behavior, since this is growth, as we move to the left, we're heading towards that horizontal asymptote at 0. So as we go to negative infinity with x, our y is going to 0. As we go to the right, to positive infinity, our graph is veering off into positive infinity for the y values. On this problem, we are rewriting this in growth or decay form and then getting the growth or decay rate and the end behavior. Let me start by putting this in a b to the t form by moving this 1 over 12 inside the parentheses with the 0.5. The main reason for doing that is so that I have this t all by itself to get that b to the t sort of look. So whatever 0.5 to the 1/12 is, that is our b value. Let's go to Desmos for that. So we've got 0.5 exponent 1 over 12 comes out to about 0.9439. So that's going to be my b value. I'm going to have to split this up now into a 1 plus or a 1 minus r sort of expression. Since this is less than 1, I'm going to have to do 1 minus something to get this. Now, what is the something? Let me go back to Desmos. And we've got 1 minus 0.9439 would tell me what I have to subtract from 1 to get 0.9439. And it looks like that's going to be 0.0561. So I can rewrite this as 1 minus 0.0561. That means that this 0.0561 is my r value. So 5.61 is my percent, and it's less than 1 for the b value, so this is a decay rate of 5.61%. Now, since this is decay, that means that as I move to the left, as x approaches negative infinity, we're actually going higher and higher on the graph because we started high and went lower. So y goes to infinity as I go to the left for x. As I move to the right then, we're getting smaller and smaller. We're getting closer to that x-axis. So we would say that y is approaching 0 in that direction. For this problem, we're trying to rewrite this in growth or decay form, get the rate, and then describe the end behavior. So let's get this in ab to the t form first. To do that, I'm going to have to take this 2/3 and I'm going to have to pull the 1/10 from the exponent into the 2/3 here, like so. And if you're not sure if this is really legal, if you raise this expression in here to the t power, you're just multiplying t by 1/10, so you would get t over 10 again. So whatever is in here, this 2/3 to the 1/10, that's my b value. Let me go to Desmos and see what that looks like. All right, so let me do parentheses, fraction, 2/3, close parentheses, there we go, raise that to the 1/10, and that comes out to 0.9602. So that's my b value. I'm going to have to split this up into a 1 minus r sort of statement because it's less than 1, so I need to subtract something from it to get this, or subtract something from 1 to get this. So if I go back to Desmos and I do 1 minus 0.9603, I see that I would need to subtract 0.0397 from 1 to get this b value. So I can rewrite this as 1 minus 0.0397. This is less than 1 for the b value, so we have a decay rate. And moving our decimal over 2, we see that we have a decay rate of 3.97%. As to the end behavior, since it's decay, we're starting high and ending at 0. So as x goes to the left to negative infinity, y is going up to positive infinity. And as x moves to positive infinity to the right, we're flattening out on the x-axis, so y is going to 0 for that one.